Hi everyone! Welcome to this video from a series on hypothesis testing. In the previous video, we built the machinery for tests based on binned data, which is a very common approach in particle physics. Today, we are going to talk about specifics of tests heading for discoveries. Will we find the SpongeBob boson? Keep watching. Up to now, we always tacitly assumed that the signal process could just add events on top of the background. We will keep this assumption throughout all this video as well. As an academic remark, though, it is fair to admit that the assumption doesn't need to hold in all situations. Of course, there can be situations when the existence of the new process predicts less events than the null hypothesis. For example, when people search for neutrino oscillations and place their detector to the oscillation minimum. Another example could be searches for the triple Higgs vertex at the LHC. The production of two Higgs bosons through this process interferes negatively with the di-Higgs production via the box of top quarks. On the other hand, most searches for beyond standard model physics, for new particles to say, comply with the assumption of just adding events on top of the standard model prediction. Most often, the new physics doesn't interfere with the standard model at all. So, from now on, we assume that the new physics we are searching for only adds events on top of the background prediction. Let's recall the test statistic T sub mu vector defined in the previous video. T sub mu vector is equal to -2 times logarithm of L of mu vector, theta vector hat of mu vector, over L of mu vector hat, theta vector hat. When aiming at a discovery, we do a test of the background-only hypothesis. In the terminology of the previous video, the background-only hypothesis predicts the signal strength mu to be equal to 0. As explained many times, the goal of a hypothesis test is to reject the hypothesis. However, we shouldn't reject the mu equal to 0 hypothesis based on the value of the test statistic T sub mu vector. We could end up in a situation that we observe much less events than the background-only hypothesis predicts, and we reject the hypothesis in favor of an alternative that predicts events in addition to the background. The reason of this paradoxical behavior is that T sub mu vector is a so-called two-sided test statistic. Its value is high regardless of whether we observe an excess or a deficit of events. To avoid the paradoxical behavior, let's modify T sub mu vector a bit to make it a one-sided test statistic, sensitive just to excesses of events and insensitive to deficits. Our definition of the one-sided test statistic for discovery is the following. Q sub 0 is equal to T sub 0 when mu hat is larger than 0, and it is equal to 0 when mu hat is lower than 0. People really call it test statistic for discovery. Its asymptotic distribution, a la Mr. Wilks, is sometimes called a half chi-square distribution. The name becomes obvious when we write the asymptotic formula down. F of Q sub 0, given the hypothesis of mu equal to 0, is equal to 1 over 2 delta function of Q0 plus 1 over 2 chi-square distribution with 1 degree of freedom of Q0. What concerns the p-value and the significance in particular, we can simplify their calculation if we realize one thing. If q sub 0 is distributed according to the chi-square distribution with 1 degree of freedom, then square root of q0 is distributed according to the standard Gaussian distribution. Therefore, we can calculate the p-value and significance with the use of the cumulative distribution of the standard Gaussian phi. P sub 0 is equal to 1 minus the cumulative distribution of q0 given the hypothesis mu equal to 0, which is approximately equal to 1 minus phi of square root of q sub 0. Z sub 0 is equal to the inverse of phi of 1 minus p sub 0, which is approximately equal to the square root of q sub 0. At this point, let's emphasize one very important thing. A discovery in particle physics has, most often, very far-reaching consequences. Therefore, people want to be extremely sure about the result, and they require a significance of at least 5 sigma. This corresponds to a probability of 2.9 times 10 to the minus 7. We are going to discuss reasons for such an extremely stringent criterion in one of the future videos. For now, just be assured that the criterion is well motivated. Let's assume we are designing a new experiment whose goal is to find the SpongeBob boson. We will need to ask funding agencies for money. Certainly, they will come back to us with a simple question. What are prospects of your experiment to find the SpongeBob boson? In other words, they want us to quantify the sensitivity of our experiment to the signal. As a measure of this sensitivity, people use the quantity z sub 0 exp, which is equal to the median of z sub 0 given the hypothesis of mu equal to 1. Please don't grumble that I call it expected and define it as a median. It's commonly called expected significance, but defining it as a median is a bit more handy. Let's rather explain what this quantity means. For this, we assume that our signal exists and that the signal strength is equal to 1. We derive distribution of the test statistic for discovery Q0 given this hypothesis. If the mu equal to 1 hypothesis is true, then the observed test statistic Q sub 0 obst is a number drawn from this PDF. As our expected significance, we define value that we would get if the observed test statistic was equal to the median of the PDF. Note that median is preferred over mean because there is an easy mapping of quantiles of the distribution of the test statistic to the quantiles of the distribution of the significance. There is an asymptotic formula for f of q0 given 1. It is a non-central chi-square distribution. However, we don't need it in practice most often. The wonderful thing is that the median significance can be approximated in a very easy way. We just evaluate a test statistic that we would get if data was exactly equal to the nominal prediction for signal plus background. This particular dataset is called the Asimov dataset. We get Median of z sub 0 given 1 is approximately equal to the square root of q sub 0a, where q sub 0a is the value of the test statistic for discovery obtained with the Asimov dataset. Where does the name Asimov come from? The writer Isaac Asimov described a situation that presidential elections in the United States become too expensive in the future. Therefore, people will do the elections by finding the most average person in the whole population, and this person will choose the president. Then, let's not be surprised if SpongeBob becomes the president. Or hasn't he in 2016 already? Anyway, the Asimov dataset is exactly this, the most average scenario that can occur if the signal hypothesis is true. One last remark. Funding agencies will be curious about the spread of the test statistic distribution. Therefore, you should add to your proposal not just the expected significance, but also some other quantiles. The most common ones are obviously quantiles of the significance corresponding to plus and minus n standard deviation of the test statistic distribution. They are given by a square root of the Asimov test statistic plus and minus n. Z0 plus minus n sigma is approximately equal to the square root of q sub 0a plus minus n. So, we are done with the topic for today. In the rest of this video, we will look at examples and we will derive some famous formulae like the S over root B significance. We will start with an example how to evaluate the expected sensitivity in a cut-and-count analysis without systematics. The model is n cut-and-count is distributed according to the Poisson distribution of n with a mean equal to mu times s plus b. We are going to use the Asimov dataset defined by n sub a is equal to s plus b. The maximum likelihood estimate mu hat is equal to 1 for this dataset. Therefore, we have L of mu hat is equal to s plus b to the power of na over na factorial times e to the minus s plus b. Since we want to discover a new particle, we are testing the hypothesis that mu is equal to 0. For the evaluation of the test statistic q0, we will need L of 0 is equal to b to the power of na over na factorial times e to the minus b. Given that mu hat is greater than 0, we are getting the following expression for the test statistic evaluated with the Asimov dataset. Q sub 0a is equal to minus 2 logarithm of b over s plus b to the power of na times e to the minus b plus s plus b. And this is equal to 2 times s plus b times a logarithm of 1 plus s over b minus s. Finally, the expected significance is median of z0 given the hypothesis of mu equal to 1 is approximately equal to the square root of the following expression: 2 times s plus b times logarithm of 1 plus s over b minus s. This formula is well known, and it is often used for optimization of cut values in cut-and-count analyses. The set of cuts yielding the highest expected significance is chosen for the analysis. Note that the formula is only valid in the Wilks asymptotic regime. Recall that this approximation holds if the number of events is about 5 or greater. Let's assume now that we have an even larger dataset and that we can approximate the Poisson distribution with a Gaussian. Mathematically written, Poisson of x with mean equal to mu times s plus b. For mu times s plus b going to infinity, approaches a Gaussian distribution of x with a mean value of mu times s plus b and with sigma equal to the square root of mu times s plus b. In contrast to the previous example, we aren't going to use the test statistic Q0. We will simply use the number of observed events instead. The corresponding p-value is calculated like this: median of the p-value given the hypothesis of mu equal to 1 is equal to the integral from n sub a to infinity Gaussian of x with mean equal to b and sigma equal to square root of b dx. And this is equal to 1 minus the cumulative distribution of a standard Gaussian phi of na minus b over square root of b. And this is equal to 1 minus phi of s over square root of b. Finally, we get median of z0 given the hypothesis of mu equal to 1 is equal to s over square root of b.